In the last section we looked at linear substitutions. Now we're going to look at substitutions more generally to see how they can help us integrate some more complicated functions. So I think it's best to just have a look at an example in this case. So if we look at this integral a for a, what we're going to try and do is we're going to try and work out what could I let u be equal to that's going to help us simplify this. And in order to see why this works, let's just say I know that u equals x squared plus 1 is going to work. Now, let's try and go through the process of the substitution then. So if I use u equals x squared plus 1, the denominator of this fraction is going to be equal to u. Now I'm going to leave 2x as it is, and you'll see why in a second. So remember, with the method of substitution, we need to replace dx with du. So we're going to work out du by dx, which is 2x. And if we rearrange this to get dx on its own, we're going to get dx is 1 over 2x du. And the key thing to realise here is that we've got 1 over the derivative of u, because the derivative of u is 2x. So what we're doing is we're effectively dividing by the derivative of u, dividing by 2x. So if we substitute this into our integral, I'm going to leave 2x as it is and u's on the bottom, and then we would times by 1 over 2x, and then we're integrating du. Now you can see that this helps us because the 2x's are going to cancel. So the key thing that I realised is if I let u be x squared plus 1, when I differentiate that, I'm going to divide by 2x, which is going to cancel that 2x up there. So I knew that I needed to let u be x squared plus 1 because its derivative was going to cancel. So now that we've cancelled the 2x's, we just end up with the integral of 1 over u du, which we know is natural log of u. And remember, we need to go back to x because we want our answer in terms of x. So we're going to just substitute in x squared plus 1 instead of u. So we've got log of x squared plus 1 plus c. And remember, the x squared plus 1 needs to be in the absolute value symbols, the modular symbols, when we integrate. Let's do a similar thing for b then. So remember, we're spotting what can u be equal to, so that when we differentiate it and we divide by that derivative, we're going to cancel with something. Well, I've spotted that if I differentiate sine x, I get cos x. So that means I'm going to let u be the denominator, 3 plus 2 sine x. And often with these substitutions, it will be letting u be the denominator. And the key thing to realise is that the top is related to the derivative of the bottom. So whenever we've got that, we let u be the denominator. So our integral is going to be, we're going to have u on the bottom, and on the top I'm going to leave cos x. So I'm going to differentiate u with respect to x to find du by dx. If I differentiate u, I'm going to get 2 cos x. Careful, we're differentiating now, so sine x differentiates to cos x. So if I rearrange this, I find that dx is equal to 1 over 2 cos x du. And 2 cos x comes from the derivative of u. So we're effectively dividing by the derivative of u. So our integral is going to become, I'm going to leave cos x on the top, and we're going to multiply by 1 over 2 cos x, divided by 2 cos x. And then you can see that this helps us because now we're going to divide, we're going to cancel the cos x's, and we're going to have integral of 1 over u times by a half du. And then at this point I'm going to take the half outside of the integral, and we're going to have a half integral of 1 over u du, and we know that the integral of 1 over u is natural log of u. But remember, we need to sub back in for u equals 3 plus 2 sine x.